So any doubt from the last class? The last topic was electric field due to an infinite plane sheet. Fatma, Jubaina, any doubt from the last class?
No, sir. It's clear.
The expression of electric field for the infinite plane sheet is sigma over 2 epsilon naught, right? This is the expression of electric field due to an infinite plane sheet, sigma by 2 epsilon. And the direction of the field is perpendicular to the sheet. The direction of electric field is perpendicular to the sheet always. So if you have this infinite plane sheet, this is the infinite plane sheet. The sheet have a charge density of plus sigma. And the direction of field due to the sheet is perpendicular to the sheet. So this is the direction of electric field. Okay. So can you plot E versus R graph? E versus R graph for this field. See here, E is sigma by 2 epsilon naught. So this E is independent of R, which means here electric field is independent of position. R is position. R is always position, separation from the field, separation from the sheet. The expression of electric field is absolutely independent. Just a minute, Afroza is joining. Yes. So for this infinite plane sheet, the expression of electric field is sigma by 2 epsilon naught. This we have derived in the previous class. This expression is absolutely independent of R. There is no R in it. So you can say that this electric field is uniform. This electric field is uniform. Uniform means independent of position. Independent of position. Which means if I take a sheet and I say that at a distance of 1 meter, the value of field is 10. At distance of 1 meter from the sheet, the value of field is 10. So at a distance of 2 meter, the value of field will remain 10. At a distance of 3 meter, the value of field remains same. Value of field will not change on changing the distance from the sheet. These types of fields are known as uniform fields, and these uniform fields are independent of position. And the direction of field is perpendicular to the surface of the sheet. If I ask you to draw E versus R graph, means electric field versus position graph. Now, since electric field is independent of position, that means on changing position, the value of field should not change. On changing position, the value of field should not change. So this graph would be a straight line. You see, you simply keep on changing R. On changing R, field will not change. The value of field is not changing. So this type of field is absolutely independent. This is known as uniform electric field for infinite range. So is this graph clear?
Yes.
Okay, let's solve a question on infinite plane sheet. This numerical is given in NCRT. So you have few sheets. Let's consider two sheets over here. This is sheet number 1. And then you have one more sheet. This is sheet number 2. This is sheet number 2. The surface charge density of sheet 1 is sigma 1. The surface charge density of sheet 2 is sigma 2. You're supposed to calculate electric field in between the sheets. Just say, let's calculate field in all three regions, in region 1, region 2, and region number. Let's calculate field in all three regions. The magnitude of electric field due to one sheet is sigma by 2 epsilon naught. Okay, Afroza, let's start from you. We have 3 parts for each one of you. So, Afroza, what is the direction of field over this point due to this first sheet? What should be the direction of field over this point due to the first sheet? It should be towards right, left. What should be the direction of field? It's left. And what about the field, direction of field in this region due to second sheet? Direction of field in this region due to second sheet? Afroza? No, it's not towards left. It's negatively charged sheet. The direction of field due to a negative charge, it's towards the charge. So for the negative charge, the direction of field would be towards the charge. So in region 1, if we solve region 1, then electric field in region 1 is simply the vector sum of electric field due to individual sheets. That's E1 plus E2. Or you can say that direction of field in region 1 is its E1, which is sigma 1 by 2 epsilon naught. The direction is to the negative x-axis. So let's say this is minus of I cap. E2, it's sigma by 2 epsilon naught. It's plus I cap. E2 is acting towards positive x-axis. While writing magnitudes, we never consider the nature of charge. Whether your surface charge density is positive or negative, we won't consider that nature here. Next, we can take this I cap by 2 epsilon naught as common, and we are left with just minus of sigma 1 plus sigma. So that is the electric field in region 1. If I repeat the same calculations in region 2, Fatma, what is the direction of field in region 2 due to this positive sheet? Is it towards right, left? What's the direction of
Left.
Due to positive sheet?
Right.
It's always away from the charge. So that's towards the right. And what about due to this negative sheet?
Right.
It's towards the sheet. Right? So both are acting towards x-axis. So in region 2, the net field is simply the vector sum of E1 and E2. So the net field in region 2 is E1, which is sigma 1 by 2 epsilon naught I cap, sigma 2 over 2 epsilon naught I cap. So in region 2, you can take I cap by 2 epsilon naught as common, and we are left with only sigma 1 plus sigma. So this is the value of electric field in region. For region 3, Jabena, direction of field in region 3 due to this positive sheet. Jabena. Direction of field in region 3 due to this positive sheet.
Left side.
Left, it's a positive sheet.
Okay, right side.
It's always away from the charge, na? So away from the sheet is this right hand side. And what about due to this negative sheet?
Left side.
So in region 3, the net field in region 3 is vector sum of E1 and E2. It's vector sum of E1 and E2. So in region 3, the field is sigma 1 is sigma 1 over 2 epsilon naught. Direction is along x-axis, so that's I cap. This E2 is along negative x-axis, so it's sigma 2 by 2 epsilon naught minus of I cap. So you can simply take I cap by 2 epsilon naught as common. So this is sigma 1 minus sigma 1 minus sigma. This is how we calculate electric field due to infinite sheets. Let's note it down. Then let's do next derivation. Did you try that assignment of Gauss law?
I just went through few questions.
Okay. And what about the rest? No response. That means you haven't tried yet. Just let me know when you have written this thing. Giovanna, I need it by Sunday. I need it by Sunday. So, Afroza, shall I rub it? I will share a number for the assignment, for the submission of assignments. It's basically counselor for your assignments, your test. That counselor is responsible even for class timings. I will share the number of that counselor with you. Your all assignments and tests, he will be managing all those things. If you have any issue with the timings of classes or any assignment or test, I will share the number of the counselor. He is responsible for all those things. So, okay, so after infinite plane sheet, the next thing is electric field. Electric field for infinite wire. Infinite wire or infinite rod. Basically, for a long one dimensional. Instead of infinite, he can use a long wire or a long rod. If it is one dimensional, then you can use the result that we will derive. So let's say you have this thing. You have a long wire. The linear charge density of the wire is lambda. This is the wire. A long wire, this wire extends from minus infinity to plus infinity. The linear charge density of this wire is lambda. You're supposed to calculate electric field at a separation r from the wire over this point. Yes, Fatma, sheet was two-dimensional. Yes, sheet is area basically. In area is two-dimensional. You're supposed to calculate electric field over this point due to this infinite thing, wire. So the first step is consider a Gaussian surface. Okay, can you suggest the shape of the Gaussian surface? The appropriate shape of the Gaussian surface for the wire?
Cylinder.
Cylinder. Right? For the straight wire, the appropriate Gaussian surface would be a cylinder. So let's consider a cylindrical Gaussian surface. The radius of the cylinder is r. The length of the cylinder is L. Wire extends from minus infinity to plus infinity. It's a long wire. Practically, long wire means this. Practically, long wire means L is very, very greater than R. Means the point at which you are calculating the value of field, the separation of that point is small as compared to the length of the wire. The length of the wire is very, very large as compared to separation. Then you can say that your wire is a long wire. Because infinitely long wire is practically not possible. When we say that wire is infinitely long, or we say it's a very long wire, that simply means the length of the wire is very large as compared to the separation at which you are supposed to calculate. L is very, very great. So let's consider a cylindrical Gaussian surface. A cylindrical Gaussian surface of length L and radius R. Fatma, can you guess the direction of electric field here? Electric field is along x-axis, y-axis, z-axis. Fatma, the direction of electric field here.
X-axis.
Yes, direction of electric field due to a positive charge is away from the charge. So the field is along positive x-axis as well as negative x-axis. So this is the direction of field. Using this field, you're supposed to calculate the flux. We need flux to the cylinder. Just like the last derivation, we will divide this cylinder into three parts: first end, second end, and then the curved surface. Afroza, can you suggest the direction of this end one? What should be the direction of end one? End one, this is first end. This is cylinder. Like the cylinder is placed along y-axis. I'm not asking about the curved surface. I'm asking about the end. This end. The direction of area vector is always perpendicular to the area. So the perpendicular to the area will be upwards. The direction of area vector is always perpendicular to the area. Perpendicular to the area for this case is upwards. So for end one, flux phi1 is, this is the direction of area. This is it. Angle between them is 90 degrees. So this is ES cos 90, which is 0. So through N1, flux is 0. Afroza, what about N2? The direction of N2? The direction of this end, Afroza. This N2, this second end. The second end of the cylinder, the lower end. Okay, it's not upwards. The direction of area vector is outwards normal. It should be perpendicular as well as out of the cylinder. Now guess what should be the direction of this area vector? This one, this particular area. This is the cylinder. I'm asking on this surface. Yes, it should be downwards. So it's not just normal. It's normal as well as outwards, away from the surface. So the flux will again be 0 because your field is along x-axis. Angle between electric field and area vector is 90 degrees. So the phi 2 is ES cos 90. It's again 0. That is second. Next, let's calculate it through curved surface. Flux through curved surface. So if you have a curved surface, then flux through this curved surface is integral of E ds. So for the curved surface, if I consider an element here, and I call this as ds, the direction of ds is along x-axis. It's very clear that E and ds are acting in same directions. So that means angle between them is 0 degree. It's EDS cos 0. So the flux is integral of EDS. Now, since this surface is a Gaussian surface, so field should be uniform. So we can take this E outside the integral. So it's integral of ds. Jubaina, what should be the value of this particular integral ds? Jubaina, the value of this integral ds.
E.
What?
E.
No, ds is a small portion of the curved surface. If I'm integrating over the entire curved surface.
E dot S.
No, I'm asking about this integral only, just ds. We did two integrals, like one surface integral for sphere and another surface integral for cylinder. If you integrate for a cylinder, then you will get the curved surface area of the cylinder. Say you are integrating over the curved surface of cylinder. So if you integrate over the curved surface, you will get curved surface area. What is curved surface area of the cylinder?
Pi r 2 pi r square.
2 pi r L. This is curved surface area of the cylinder. So if you're integrating over the curved surface, you will get 2 pi r. Right. Now, in the next step, let's calculate total flux. Let's calculate total flux. So the total flux would be the sum of flux due to first surface, flux due to second surface, and flux due to third surface. That's the total flux to a cylinder. So due to first surface, flux is 0. Second surface, flux is 0. Third surface, flux is E into 2 pi r. So that is the total flux through the cylinder, which is E multiplied by 2 pi rl. That is equation number. So is it clear or doubts? Any doubt? Up to this,
Sir, we are finding the electric field for the wire or the cylinder.
we are calculating field for the wire. But to calculate that field, you need flux. And you have to apply Gauss law. To apply Gauss law, you need a closed surface. That's why we are taking the cylinder. We are calculating flux passing through the cylinder. And using that flux, we can calculate electric field. See, the concept of this derivation is, while you can calculate flux through two methods. You can calculate flux using this definition of electric field. You can also calculate flux through Gauss law. So we calculate flux by the two methods. First we calculate using field, then we calculate the same flux using Gauss law. Then we equate those two flux. By equating those two flux, you can get the value of electric. Gaussian surface is important because you can't use Gauss law for an open surface. You can use Gauss law even if your surface is closed. Got it?
Yes, sir.
Just note it down. Please note it. Okay, the next is You can also calculate this flux using Gauss law. You can Gauss law. So Gauss law says that phi is Q enclosed divided by epsilon. So that's equation number 5. Okay, Fatima. What's the total length of the wire? Fatima. What?
Infinity.
Yes, the total length is infinite. What portion of the wire is enclosed by the cylinder? What length of the wire is enclosed by cylinder?
L.
L. So this Q enclosed is basically Q enclosed is charge on length L of cylinder. Length of wire. Because charge is distributed over the wire, not on the cylinder. So we can write this lambda as the charge divided by length. So we can write linear charge density is Q enclosed, and this Q enclosed charge is on length L. So I can write this lambda as Q enclosed L. Next, you can write your Q enclosed as lambda L. That's equation number 6. You can easily substitute 6th and 5th. On substituting 6th and 5th, you will get that your flux is lambda L over epsilon. So this is flux due to long wire. This is equation number 7. Next, you can compare 7th and 4th. In equation number 4, this equation number 4 and 7, we are calculating the same flux. But the approaches are different. In 4th, we calculated flux using definition of field. But in 7th, we are calculating flux using simple Gauss law. So, but in both equations, we are calculating the same flux through the cylinder. So we can equate 4 and 7. When you equate them, you will get E multiplied by 2 pi RL, which is lambda L over epsilon. This L will cancel this L, and you will get that E is lambda over 2 pi epsilon naught. So this is electric field. E is lambda over 2 pi epsilon naught. So you can say that electric field due to this long wire is inversely proportional. This is inversely proportional to the separation from the wire. And the direction of field is perpendicular. So in vector form, yes, Fatma, usually this derivation comes directly in the exam. Usually it's a 3-marker question. So in vector form, this electric field E is, it's lambda over 2 pi epsilon naught R n cap. Today I will finish chapter number 1. So by tomorrow I will share an assignment based on your previous year questions, the type of questions that has been asked in your exam. So you'll get a good idea of the type of questions that can be asked. So if I plot E versus R graph, this is R and this is electric field E. So the graph will be parallel. Hyperbolic graph. That means on increasing R, the value of E will decrease. Just note this.
Sir, R is position or radius here?
R is always position. It's separation from the wire. There R is separation from the wire. And if you talk about cylinder, then this is radius of cylinder. But actually this is separation from the wire. So I shall. Jubena, shall I rub it? Jubena, shall I rub this?
Okay, sir.
Let's solve a numerical on the same concept. Let's take two long wire having linear charge density lambda 1 and minus lambda. The linear charge densities are lambda 1 and minus of lambda. We consider a point here. This point is at a separation T from both the wires. We have to calculate electric field at T. So at P, both the wires will generate electric field. So first of all, we take direction of fields at P due to both the wires. So first wire is positive. So field at P due to first wire, let's call this as wire number 1 and this as wire number 2. So the direction of field is simply away from the wire. So it's acting away from the wire, that's E1. Due to second wire, the direction of field is towards the wire. This is the direction of field due to second wire, that's E. Both the fields are acting in same direction, you can easily add them. So net field at P, so the net field at point P is just vector sum of E1 and E2. For the net field at P, just vectorically add E1 and E2. E1 is lambda 1 over 2 epsilon naught D. The direction is along x-axis, so let's put an I cap. Due to second, that it's lambda 2 by 2 pi epsilon naught D. Sorry, pi is missing. It's 2 pi epsilon naught. And again, the direction is towards positive x-axis. Let's put an I cap. Next, you can just take common this I cap by 2 pi epsilon naught is common. In fact, D is common. You are left with just lambda 1 plus lambda. In the same method, you can calculate field in this region or in this region, the way we have done for infinite regions. Is it clear? Okay. Please note it, then we'll move on to the next one. The last derivation due to a sphere. I can't skip sphere because to teach potential and capacitance, I need electric field of sphere. You should know what is sphere, how to calculate field of the sphere. Jabana, Afroza, shall I rub it? Now, when we talk about sphere, we can divide sphere into two categories. We can have two types of sphere. One sphere where charge is distributed only on the outer surface. Charge is distributed only on the outer surface. Charge distributed on outer surface. Distributed on the outer surface. Let's say the radius of the sphere is capital R. So you have some charge Q which is distributed, uniformly distributed on the outer surface. The examples of this type of charge configuration include if you have an hollow sphere. Now, since sphere is hollow, there is no material inside the sphere, so charge will distribute only on the outer surface. It could be hollow conducting. It could be hollow non-conducting. It won't matter if your sphere is hollow, whether it's conducting or non-conducting, you will get same type of charge configuration. It could be hollow conducting or it could be hollow non-conducting. This could also be a solid conducting sphere. This could even be a solid conducting sphere. So whether your sphere is hollow conducting or a hollow non-conducting, or even if it is solid conducting sphere, even in conductors, charge is distributed only on the surface. If you take a solid sphere of copper and you charge that solid sphere, charge will reside only on the outer surface. Charge cannot penetrate a conductor. The second type of sphere could be a sphere where charge is distributed throughout the volume. Here, charge is distributed throughout the volume of the sphere, everywhere. So, charge distributed throughout volume. Throughout volume of the sphere. And the example of these types of sphere includes solid non-conducting sphere. Solid non-conducting sphere. Because if you have a solid conducting sphere, then charge will reside only on the outer surface. The solid conducting sphere is this example. But if you have a solid non-conducting sphere, then charge will be distributed throughout the volume of the sphere. So these are the two types of sphere. This type of sphere is not included in CRT. It's not part of standard CBSE syllabus. You have to do only this. This sphere is very important. You will study this sphere even in potential. You will study this sphere even in capacity. You need this particular sphere. Next, let's calculate electric field. Let's calculate electric field due to hollow conducting, non-conducting, or solid conducting sphere. Solid conducting sphere. So let's calculate first case one. If point lies outside the sphere. It's a very easy calculation. If point lies outside the sphere. Outside the sphere. So let's consider a sphere. This is the sphere. The radius of the sphere is capital R. Some charge Q is uniformly distributed over the surface of the sphere. We're supposed to calculate field over this point. This is the radius of the sphere. So we're supposed to calculate field at a separation R from the sphere. This is R. This whole is R. So to calculate field over this point P, the first step is choose an appropriate Gaussian surface. So you can easily guess that if your sphere is, if your charge distribution is spherical, then your Gaussian surface should be a sphere. So I consider a sphere of radius R. So this is my Gaussian surface. This in yellow color is my Gaussian surface. The radius of the Gaussian surface is smaller. So consider a spherical Gaussian surface at point P. So at the point P, we have considered a spherical Gaussian surface. So first of all, let's calculate flux through the surface. Flux through Gaussian surface. So through the Gaussian surface, the expression of flux will be just fair. So we can use closed integral. It's closed integral of E dot ds. C is a positive charge. The direction of field is away from the charge. If I consider a small element here, then the direction of small ds elements again outputs. So E and n cap are acting in same direction. So you can simply take that your flux is its closed integral of E ds cos 0. Next, you can take this E outside this integral sign. So this is E, its closed integral of ds. You can integrate this ds over the entire Gaussian surface. You will get phi is E into 4 pi r square. Remember, I'm not integrating on the surface of sphere. If I would have integrated on the surface of sphere, then area would be 4 pi capital R square. In fact, I'm integrating over the surface of Gaussian surface. So that's why this is 4 pi small r square. That's my first equation. Next, we can easily calculate the same flux using Gauss law. So here the phi is, the charge enclosed is Q only. So standard Gauss law is phi is Q enclosed by epsilon naught. This is the Gaussian surface. Gaussian surface includes the complete sphere. So you can say that your Q enclosed in this particular case is equal to Q only. So the phi is Q over epsilon naught. That's equation. You can easily equate 1 and 2. If you equate 1 and 2, it's equating 1 and 2. If we equate 1 and 2, then you will get E 4 pi r square is Q by epsilon. So we can write this E as the value of electric field is it's Q by 4 pi epsilon naught r square. So your field is inversely proportional to r square. This is the value of electric field. E is inversely proportional to r square. So see, the expression is same as that of a point charge. That's why in the first lecture of Coulomb's law, I have written that Coulomb's law is valid either for a point charge or for a sphere. So the behavior of a sphere is just like a point charge. That's why the result of sphere and point charges will always be same. So is it clear up to this first case? The second is if point lies on the surface of sphere. Can you guess the radius of the Gaussian surface now? If point lies on the surface of sphere, say if point lies here, then the Gaussian surface will coincide with the surface of the sphere, right? Because you will take a Gaussian surface which is passing through the surface of spheres, which is passing through the point. So if I call this as equation number 3, so here small r would be equal to capital R. The whole calculation would be same. Just instead of small r, you will use capital R. So on the surface, you just substitute small r equal to capital R in 3 and we get electric field on the surface is Q by 4 pi epsilon naught capital R square. This is the expression of field. Just one more thing. Let's say this is equation number 4. Fatma, can you calculate sigma here, surface charge density of sphere? The charge over the sphere is Q, the radius of the sphere is capital R. So Fatma, what is the surface charge density of the sphere, the value of the sigma for the sphere? Fatma.
Q enclosed by the area.
And what is the area of the sphere? Q enclosed is basically Q.
4 pi r square.
Small r or capital R?
Small r.
No. Charge, where is this charge distributed? It's distributed on Gaussian surface or it's distributed on sphere? Fatma.
Here.
Sphere. And what is the radius of sphere?
Capital R.
So it should be Q by 4 pi r square, not small r square, right? This is equation number 5. If I substitute this 5 in 4, Means instead of this q by 4 pi r square, I use sigma. Jubena, what should be the value of field on the surface? If I use this 5 in 4, this q by 4 pi r square, if I use this as sigma, then what should be the value of field on the surface?
R square sigma by epsilon.
This is the electric field on the surface of the sphere, sigma by epsilon. So you can either write this in terms of q by 4 pi epsilon naught r square, or you can write this in terms of sigma, q by epsilon, sigma by epsilon. Please note it, then we'll calculate field inside the sphere. Okay. Afroza, shall I rub it? Okay. So let's do case 3. If point lies inside the sphere, if point lies inside the sphere, if point lies somewhat here, inside the sphere. Now, can you guess, Afroza, what should be the Q enclosed, value of Q enclosed now? The point is inside, your Gaussian surface is inside. What should be the value of Q enclosed now, Afroza? Q enclosed charge. R is radius. The charge is distributed on the sphere. I took a Gaussian surface inside the sphere. The radius of Gaussian surface is less than capital R. I'm just asking about the charge inside the Gaussian surface. How much charge is there inside the Gaussian surface? Afroza. Okay. No, it's not Q. Jabena, can you guess the charge inside the Gaussian surface now?
Is it flex multiplied by epsilon?
No. Fatma? Okay, just check. Where is this charge distributed? This charge is distributed on the surface or inside? This is distributed on the surface, not inside the sphere. The whole of this charge is distributed only on the surface, not inside the sphere. So if I take a point inside the sphere, then the charge over that point is zero.
Zero.
It would be zero. If I consider a point inside the sphere, then the charge inside this point should be zero. Q enclosed should be zero in this case. If Q enclosed is zero, that means electric field inside the sphere is zero. Got it?
Yes.
Okay. So if you consider field inside the sphere, then electric field inside the sphere is always. The next is you're supposed to plot E versus R graph again. But now, why it is zero again? Afroza, where is this charge distributed? The charge Q. This charge Q is distributed only on the surface of the sphere, right? If this is the sphere, then whole of the charge is distributed only on the outer surface. If I consider a sphere inside it, there is no charge inside the surface. That's why Q enclosed is zero. There is no charge inside the surface. All the charge is distributed only on the surface, outer surface. Now the next task is to plot E versus R graph. To plot E versus R graph. This is R and this is E. This is R equal to capital R. R equal to capital R means your point is on surface. R is less than capital R. So what you understand by R is less than capital R? This point is inside or this is outside? If this is the surface of the sphere, if I'm saying that R is less than capital R, this point is inside the sphere or outside the sphere? This is inside. Less than R, less than capital R. The radius of the sphere is capital R. So if I'm saying R equal to capital R, that means on the surface. If I'm saying R is less than capital R, then point will lie inside. And if I'm saying that R is capital greater than capital R, then this point will lie outside. Okay. Now let's plot the graph. What is the value of field inside the sphere? Inside your electric field is 0. So this graph will be parallel to x-axis. Since value of field is 0 here, it's 0. On the surface, it increases. On the surface, the value of field increases. It becomes sigma by epsilon naught on the surface. And then what outside? Outside, the field varies as 1 by r square. Means as you increase distance, value of field will decrease. So outside the sphere, this will go like this is inside and this is E outside, which is inversely proportional to r square. So this is 0. Then field increases on the surface, then it again decreases outside. So this is how we plot E versus R. So is it clear?
Yes.
Okay, then note it please.
So for this derivation, if it come for exam, we have to draw even this graph too.
Or even this graph. And these are very famous 1 marker and 2 marker questions. Plot E versus R graph for a straight line. Plot E versus R graph for a sphere. We will even use plot graph for the sphere for potential and capacitance of this. So shall I rub it? Okay. The next thing is the chapter 1 is finished. Now it's up to you to solve assignments. I'm mentioning some important questions from the assignments which are even there in NCERT. So the question is, by tomorrow, try these questions, at least question number 2. Question number 6. And question number 1. At least solve these 3 questions. Although answers are mentioned, but at least try to solve these questions. These 2 questions are very important. These are solid examples of NCERT. They are even in NCERT. Okay. Okay, by evening I will share like question number 2. I'm giving some hint for question number 2. Okay. In question number 2, cube is given. and you're supposed to calculate flux through the cube. The hint here is calculate flux for each of the individual phase. Calculate flux for each phase. Means if you divide this left, right, top, bottom, front, and back faces, then you're supposed to calculate flux due to each phase. Calculate flux due to each phase and then add them up. For question number 6, a cylinder is given. This is end 1, this is end 2, and this is curved surface. To calculate flux through cylinder, divide this cylinder into 3 parts. First, try to calculate flux through end 1, then flux through end 2, and then flux through the curved surface, and then calculate total flux. The way we did in 2 derivations, in first and second derivation, we have calculated flux through the cylinder just by dividing cylinder into 2 ends and a curved surface. In the same way, just try these questions using the same. By evening, I will share the solutions of these questions by 5 or 6 p.m. as per your parent timing. By 6 p.m. I will share the solutions, even the solutions of the questions. But till then, at least try all questions at least once. If you have any issue, we can discuss it tomorrow. So tomorrow we'll discuss these questions and we'll start chapter number 2. We'll discuss your doubts of chapter number 1 and then we'll start chapter number 2. Let's stop here, just a 1-hour class. Tomorrow it would be a 2-hour class. Okay, thank you. Allah Hafiz.